Today, we're doing calculus, chapter 3, section 3, rates of change in real life. I'm your host, Dr. D. Okay, let's get started here. So, basically today we're going to be dealing with the same concepts that we've been dealing with all year. The concept of rate of change at an exact instant. But we're going to be applying them to all sorts of economic and scientific and biological applications. So it's going to be a major blast. We just love word problems.
Oh no! Someone peed in my pants!
Okay. So, first thing, we've got this particle that's traveling from position 1 to position 2 between time 1 and time 2. So one particular time it's at a position, and then it moves upward in some distance in feet over some length of time. So as I go to the right, time is going forward, and as I go up, the position of the particle is moving. Now, if I take the slope between position 1 and position 2, what I have is how far is the particle going, rise, divided by how much time is it taking to move, that's run. So rise over run is velocity, change in position, divided by change in time. Now, that would be feet divided by seconds, feet per second. Now, that's the average velocity from position 1 to position 2. Now, what if I wanted the instantaneous velocity right here at position 1? Well, now I need the derivative of the function with respect to time, ds dt, or s prime of t, which is the limit as delta t approaches 0 of the average velocity. And notice the curve is getting steeper and steeper as you go. So the instantaneous velocity at time 1 is much less than the instantaneous velocity at time 2. And the average velocity would be somewhere in between the two. So let's cruise onward and actually work with some problems here. So first we're going to check out example 1 on page 199. We've got the position of a particle is given by the equation s of t equals t cubed minus 6t squared plus 9t. Okay. So notice they're asking for the velocity at any time. Well, the velocity is always the derivative of displacement or distance. So what I want is s, well, let's say like this. Velocity at any particular time is going to equal s prime of t, which equals the derivative of this function, which is 3t squared minus 12t plus 9. So there's my velocity at any time. Now, I could simplify this a little bit, like factor out a 3. And then if I wanted to, I could even factor this. What multiplies get 3, that adds get -4. That would be a -3, -1. So 3 times the quantity t minus 3t minus 1. All right, so this is velocity as a function of time. Okay. Now, what's the velocity after 2 seconds? Well, the velocity at exactly 2 seconds is going to equal 3 times 2 minus 3 times 2 minus 1. Well, 2 minus 3 is negative 1, 2 minus 1 is positive 1, so we've got the velocity at 2 seconds being negative 3 feet per second. What does that mean? Well, that means it's going 3 feet per second backward. Or downward. A lot of times velocity going down is negative. So 3 feet per second, we'll just say backward. Now if it was positive 3 feet per second, that'd be 3 feet per second forward. Remember, velocity has both a magnitude and a direction. Now what's the velocity at exactly 4 seconds? Well, at 4 seconds, it's going to be 4 minus 3 is 1, 4 minus 1 is 3, so we've got 3 times 1 times 3 is 9 feet per second. And that's 9 feet per second forward. Okay, then they ask us, when is the particle at rest? Well, if the particle is at rest, then that basically says that the velocity equals 0. So if the velocity equals 0, then what that's saying is 3 times t minus 3 times t minus 1 equals 0. Notice how handy it was that I factored this.
And now for something completely different.
Okay, so here, t equals 3 or t equals 1. Or let's just say t equals 1 or t equals 3. What's that mean? Well, at 1 second after this particle begins moving, it stops and changes direction. And at 3 seconds after the particle starts to move, it stops again and goes back the other direction. So notice we see that in the beginning the particle is moving forward, because when t equals 0, you've got 3 times negative 1, which is a positive 9. So the particle begins moving in the positive direction, or toward the right. Then at 1 second, it stops and goes back left. Notice at 2 seconds, it's going left still, or backward. And then at 3 seconds, it stops and goes forward again. And notice by 4 seconds, it's going 9 feet per second in the forward direction. Okay. Then the total distance traveled by the particle during the first 5 seconds. Okay, total distance. That's not total displacement. See, if I wanted displacement, let's look what happens here. If I go s of 5, that means I put 5 seconds in for the time, and I find the distance, or I find the displacement, I should say. So this is going to be 5 cubed minus 6 times 5 squared plus 9 times 5, which equals 125 minus 6 times 25, which is 150, plus 45. So we've got negative 25 plus 45 is 20. What this says is, this particle in 5 seconds ended up 20 feet further ahead than where it started. that's its displacement. Displacement is 20 feet. So that means if it goes forward, then backward, then forward again, and it stops at 5 seconds, then the total distance, or the total displacement, was 20 feet. That's not the distance though, because distance counts forward, and then it counts backward, adds that up, and then counts forward again, adds that up. So displacement, or for distance, what we have to do is say, how far did it go in the first second? Then how far did it go from second 1 to second 3? And then how far did it go from second 3 to second 5? Okay, so let's check that out. Let's get rid of this stuff for now. Okay, so the distance from t equals 0 to t equals 1. Let's put that. Then the distance from t equals 1 to t equals 3. And then the distance from t equals 3 to t equals 5. All right, so if I'm going from 0 to 1, I put 0 in, well, basically this is going to be s of 1 minus s of 0. And that's going to be 1 plus 9 is 10, minus 6 is 4. So that's going to be 4 minus 0, which equals 4 feet. And this will be forward. Okay, now, the distance from time 1 second to time 3 seconds, well, that's going to be s of 3 minus s of 1. Which if I put a 3 in here, I've got 3 cubed, which is 27, minus 6 times 3 squared, which is 6 times 9, 54. So 27 minus 54 is negative 27, plus 9 times 3 is 27. So that it's going to be 0 minus s of 1, which is going to be 4. So then it went 4 feet backward. Okay, now distance from 3 to 5 is going to be s of 5 minus s of 3, which is going to be 20 feet. That's s of 5, we already figured that out, minus s of 3, which is 0. And so that's going to be 20 feet forward. Now, notice the displacement. If I go 4 forward, 4 backward, 20 forward, the total displacement is just 20. Because I went 4, then 20. But the distance is going to be 4 plus 4 plus 20. So the displacement is 20 feet. The distance is 28 feet. So that is the difference between distance and displacement. Displacement is just how far have I progressed. Distance is how far did I travel, forward or backward. So let's say I'm a football player and I run 20 yards forward and I get tackled. Or another football player runs 10 yards back, then 15 yards forward, then another 10 yards back, and then 5 yards forward. Well, he still only covered the 20 feet, or 20 meters, 20 yards. But so his displacement is the same. He still only gained that much yardage. But if you were to count his total distance that he traveled, it would be a lot more. So you need to remember the difference between displacement, which is basically the net gain in distance, versus total distance, which counts forward and backward. Now, if we're only going one direction, then displacement and distance will be the same. Okay, cruising onward. All right, example 2. We've got rho. It's not a P, it's a rho. That's a Greek letter that basically stands for density. Now, in this situation, we've got a rod that gets denser and denser as you go from left to right. So this density is a function of distance. So basically it's the change in mass divided by the change in distance. Now if I want the instantaneous rate of change of density, then that would be the limit as the distance approaches 0 of delta m over delta x, which is dm dx. So basically what we're looking at is the density changes at a rate, an instantaneous rate of dm dx. So if my mass equals the square root of x, what I want is rho at these two different distances on the rod. Okay, so first thing I do is if I want dm dx, then basically I need the derivative of mass. So mass is going to equal x to the 1/2 power. That means dm dx equals 1/2 x to the negative 1/2 power, which equals 1 over 2 square root of x. Okay, now, at 1 meter, well, let's just go rho, here, get the notation right. Rho of 1 meter is going to equal dm dx, where x equals 1, which is going to equal 1 over 2 times square root of 1, which equals 1/2. And what are our units? Mass per distance. And what's our mass? Kilograms? Yes. Kilograms per meter. So 0.5 kilograms per meter. Now, obviously this rod is in France because kilograms per meter. We don't know what that is in this country. Okay, now rho of 2 meters is going to equal dm dx when x equals 2, which is going to equal 1 over 2 square root of 2 kilograms per meter, which ends up equaling approximately 0.48 kilograms per meter. So notice as I move from left to right on this rod, the rate of change of density is getting smaller, although the density itself is getting larger. So basically, what's that curve look like? It looks like this. Notice it's getting less and less steep, but it's still going up. Okay, cruising onward. Let's get missed it. Forgot to get rid of that when we first started. But now we're rid of it and we're all happy. Okay. Next example, we're going to jump to example 5. What we have in example 5 is an example from thermodynamics. We've got beta, which, once again, Greek letter. It's not a B. I didn't overshoot the B here. It's the way you write a beta. That is the isothermal compressibility coefficient. Isothermal compressibility. What that means is the iso means it doesn't change, thermal's temperature. So the compressibility of this particular gas when the temperature stays constant. Now, beta equals -1 over V, the volume, -1 over volume times dV dP, which is the rate of change of volume with respect to pressure. Okay, it's how much is the volume increasing as the pressure increases, or how much is the volume decreasing as the pressure decreases. And here's another relationship. Volume equals 5.3 over P. So what that tells us is volume and pressure are inversely proportional, which we basically already knew because we knew PV is approximately nRT, which means as volume, well, let's say as pressure goes up, volume goes down. See, as the denominator of the fraction gets bigger, the entire fraction gets smaller. So if you compress something, its volume is going down. Now, different gases compress at different rates, and this one at 25 degrees C has this relationship that pressure times volume equals a constant 5.3. So, what we want is beta when the pressure is 50 kilopascals. Once again, this gas is in France because we don't even use kilopascals in this country. What do we measure pressure in this country? Right, good old pounds per square inch. Okay, so we're actually using kilopascals. Okay, so here we go. I want beta when P equals 50 kilopascals. That means I need to find the volume at that point. And so, actually, before we do that, let's find dV dP using this. So, if V equals 5.3 over P, we could really write that 5.3 P to the -1. That's 5.3 over P. So now I want the derivative of volume with respect to pressure. So dV dP. Oh, and one thing real quick, volume is always a capital V. Velocity is always a lowercase v. Okay, dV dP then equals -5.3 times P to the -2. Or we could just write it negative 5.3 over p squared. Now, notice what's happening here. The volume, the dV dP, the change in volume as pressure goes up, is negative. That means that the rate of change of volume is going to be getting smaller as pressure goes up. Okay, so we found dV dP. So I can just plug that right in, dV dP. At what pressure? Well, at 50 kilopascals. Now, what is volume when pressure is 50 kilopascals? So we've got to go volume at the pressure of 50 kilopascals is, well, I plug in 50 here, so it's going to be 5.3 over 50, which is going to equal, oh, they didn't even calculate it out. Okay, so we'll just leave 5.3 over 50. All right, so now I've got beta equals negative 1 over v. Well, here's v right here. So if I go negative 1 over v, that just makes it negative 50 over 5.3. See, if v is 5.3 over 50, then negative 1 over it just flips it. Okay, times dV dt, or dV dP. And dV dP, what we found out was it's negative 5.3 over p squared. And we said p is 50 kilopascals. So this becomes negative 5.3 over 50 squared. Okay, so that's what we're going to do then, is multiply by the dV dP, negative 5.3 over 50 squared. So there's my beta. And that's going to end up being positive 50 over 2500 is 1/5, and the 5.3's cancel. So we're left with exactly 1/5, which would be 0.2 Oh, no, I'm sorry. It's not 1/5. It's 1/50th, because only 1 0 cancels. So 1/50th, and 1/50th is 0.02. And this is your beta, which is in cubic meters per kilopascal per cubic meter. Cubic meter per kilopascal per cubic meter. So that's our beta, 0.02 cubic meter per kilopascal per cubic meter. All right, so basically that wasn't as difficult as it looked. You're just not used to dealing with kilopascals and cubic meters and all that junk, isothermal compressibility, all that stuff. All we did was we took the derivative of 5.3 over p, and we got negative 5.3 over p squared. We plugged in our p, and we got v. So we got our volume, we got our pressure, and then, I'm sorry, not our pressure, but our change in volume with respect to pressure. And then we just plugged everything in for beta and ran them up. So that's it. Cruising onward. All right, this next example is an example of population growth, which is a huge application of rate of change, because we're interested in how fast something changes when we're talking about population. How fast is the population growing? So P of T is the population of some particular animal or plant or species. In this case, we're talking about the population of a bacteria colony at any time t. Now, delta P divided by delta T is the change in population divided by the change in time, which is the average change in population per unit time. The average rate of change. Now that's not as valuable as the instantaneous change in population per unit time, which this would be called the growth rate at a particular time. And that's what we want to know, is how fast is this scum growing? So like, how important is it that I get the medicine before this population grows so fast that it kills me? Okay, now, our population is going to equal P sub O e to the t. What's P sub O? It's the initial population. P sub O, always the initial population. And that means the population at time equals 0. Okay, what they want us to find out is the growth rate at 4 hours after. Now you've got 100 cells to begin with, and you want to know what the growth rate is 4 hours after you let those 100 cells multiply. Okay, so what we're trying to do is get, well, let's just plug in what we know. So we know the population, well, let's just, population at time 0 equals 100 cells. So that means that we could write P equals 100 e to the t. Now, the t equals 4 hours, you don't want to put that in right away, because if you do, you have 100 e to the 4th, which is a constant. Now when you take the derivative of a constant, you get 0. What you want to do is you want to take the derivative of population, dp dt, with t in there. Okay, so dp dt, the derivative of 100e to the t. Well, what is that? Well, the derivative of e to the t is e to the t. Derivative of 100e to the t is still 100e to the t. Now, if I want to know the growth rate at 4 hours, then what I want is dp dt at t equals 4. Or I also could write that as p prime of t, not p prime of 4. See, p prime of t is dp dt, but I want p prime of 4. Well, what do? I go to dp dt, plug in 4 for t, and I get 100 e to the 4th. And that's going to be approximately, see, e to the 4th so 5459.8. So we'll say 5460. 5,460. Now what are the units? Well, it's the rate of change of population per unit time. So that means 5,460 cells per, what time are we talking about? Hour. Yeah, right. All right, so when we first started, the rate of growth at time equals 0, the rate of growth was 100 e to the 0, which is just 100. So these cells started out multiplying at just 100 cells per hour. After 4 hours, they're multiplying at 5,460 cells per hour and increasing rapidly. So you want to get to the drugstore quickly, get your drugs, kill this bacteria before it kills you, because it looks like it's going to kill you pretty fast. Okay, so basically, that's all we have to do, is take functions, take the derivative of them, and then find out their value at particular times or particular distances. So what we're doing is finding the instantaneous rate of change by taking the derivative of a function at a given time. That's it. Have fun with these.